Hi class, let's talk about Chapter 2. Chapter 2 is about chemistry. We need to talk about chemistry before we can talk about biology. And in this chapter, we're also going to talk about water and carbon. Keep in mind that all reactions typically occur in water, and carbon is the backbone of all organic molecules, such as fats and sugars, nucleic acids, and proteins. In this chapter, we're going to talk about the structure of atoms, ions, and molecules. We'll talk about how they're bonded together and how reactions occur. Later on in this chapter, we'll talk about the unique properties of water, current models to explain the chemical evolution, and then, of course, carbon. And carbon is found in all organic molecules. You know, the molecules that make life. So what is chemical evolution? Chemical evolution is the leading explanation for the origin of life on Earth. With all that initial energy to form Earth, energy was used to form these different atoms, and these atoms combined together to form molecules. So in other words, chemical evolution means it's the evolution of going from small molecules to very large complex molecules. And this was done through evolution by natural selection. So it says a descendant of the original molecule became metabolically active, and once it acquired a membrane, then it eventually became the first cell, and this is how life began. Is the theory of chemical evolution possible, and what is the evidence? So to begin this question, let's start off with looking at atoms and molecules. There's 4 types of atoms that you need to know, and really they're very important because they make up 96% of all matter of organisms, and that is hydrogen, carbon, nitrogen, and oxygen. My little mnemonic device for remembering them is CHON, you know, like in Cheech and Chong. So CHON means carbon, hydrogen, oxygen, and nitrogen, and that's how I remember it. It's like Chong, the guy that used to ride around in a car with Cheech in LA smoking pot. Okay, so to understand these simple substances and how they evolved into these larger molecules, we need to understand the physical structure of each of these atoms. First of all, atoms are composed of 3 subatomic particles: protons, neutrons, and electrons. Protons have a positive charge, neutrons have a neutral charge, and electrons have a negative charge. I simply remember that protons begins with the letter P, and P is also for positive. And positive charges have to be balanced with negative charges, so electrons must have a negative charge. Protons and neutrons are located in the nucleus, and electrons orbit around the nucleus. In Figure 2.1, we can use the analogy of a football field and a football. So the football would be the nucleus, you know, the nucleus that contains the protons and neutrons. And then electrons would be orbiting around the stadium and around the football. All elements or all atoms have an atomic number. So the atomic number is the number of protons. And every atom has a unique number of protons. So if an atom has the same atomic number, it means it belongs to the same element. This will be a test question. What makes every atom unique? It's definitely the atomic number, not the number of protons. I love this periodic table in Figure 2.2. It shows the first 3 rows, and the first 3 rows contains CHON. That's carbon, hydrogen, oxygen, and nitrogen, those elements that make up 96% of life. In each of the squares, you're going to see a symbol, C like for carbon, N for nitrogen, O for oxygen, and then you're going to see 2 numbers, a large number and a small number. The small number represents the atomic number, or the number of protons, and the large number represents the mass number, which is the number of protons and the number of neutrons found in the nucleus. Keep in mind that protons have a positive charge and electrons have a negative charge. So whatever number of protons you have to have the same number of electrons. And when you do that, then the entire atom is electrically neutral because protons and electrons balance each other out. The mass number again is the number of protons and neutrons, and they're both found in the nucleus. Each one has a mass of 1 and it's measured in Daltons. So keep in mind when we talk about the mass number, we're not including electrons. And the reason is that the mass of electrons is so small, it is typically ignored. So therefore the mass number again is equal to the number of protons and the number of neutrons. There's also isotopes. So if you look at the word isotope, the prefix iso means similar but not identical. So you can have isotopes of an element, and one of the most famous ones is carbon. So the typical one is carbon-12. Carbon-12 has 6 protons and 6 neutrons, but there's also carbon-13 and 14. Carbon-13 has 7 neutrons and carbon-14 has 8 neutrons. So notice that they all have the same number of protons, which makes them the same element. But notice that the number of neutrons is changing, and this is called isotopes. So when you look at the atomic weight, oftentimes for the mass number, you won't see a whole number, but instead something like 12.01 for carbon. So how did they get the number 12.01? Well, scientists measured all carbon atoms, including the isotopes. That is, those atoms that have more neutrons than normal. And when they average them all out, you get a number past the decimal point. And that's why you see something like 12.01. Most isotopes are stable, but some are unstable, and they're called radioactive isotopes, and they decay over time. So when we use carbon-14 to actually date fossils, we know the date because carbon-14 decays over time. Now let's concentrate on electrons. Remember, electrons orbit around the nucleus, and electrons travel in pairs, and these pairs are called orbitals, and they're found in shells. But for this class, I really want you to focus upon the shells. The first shell, the second, and the third. The first shell is found closest to the nucleus, and it holds up to 2 electrons. The second and the third shells are the second and third rings, where you'll see electrons travel in pairs. And the second and third shells hold up to 8 electrons, and this is often called the octet rule. Octet means that the second and third shells can hold up to 8 electrons. So it says here each electron shell contains a specific number of orbitals, because remember, when we talk about an orbital, we're talking about 2 electrons circling the nucleus together. But what's important for me is that you remember that the first shell holds up to 2 electrons and the second and the third shell hold up to 8 electrons. The electrons of an atom fill from the innermost shells first, and then they fill out to the outer shells. The outermost shell of an atom is called a valence shell, and the electrons in that shell are called valence electrons. And then the number of unpaired valence electrons are called the valence. Now that's sort of a tricky way to explain something. An easier way to say is how many more electrons are needed to fill that shell so that that shell or that atom is stable. So for example, let's look at hydrogen. Hydrogen is found in the first row of the periodic table, and that means it only has 1 shell. And hydrogen has 1 electron, so the first shell is its valence shell, and there's 1 electron there, so that's its valence electron. But how many more electrons does hydrogen need to be stable in the first shell? Well, it needs 1 more electron because the first shell holds 2 electrons. So Again, its valence shell is the first shell, the valence electron is 1, and its valence is 1. Let's take a look at oxygen. Oxygen has 2 shells, so its valence shell is the second shell because that's the outermost shell. How many electrons are in the outermost shell? Well, there's 6. So the valence electrons are 6. And what is the valence? Well, we can say it's the number of unpaired electrons, but another way of looking at it is how many electrons more does oxygen need to have 8 so that it's stable? And the answer is 8 minus 6, which is 2. It needs 2 more electrons. So the valence of oxygen is 2. I love figure 2.3 because it shows the first 3 rows of the periodic table. I just talked about oxygen, but let's look at nitrogen. Nitrogen is found on the second row of the periodic table, and notice it too has 2 shells. The first shell has 2 electrons, and then the second shell is the outermost shell, or its valence shell. And if I count up the number of electrons, I see 2, 3, 4, and 5. So there's a total of 5 electrons, so those are the valence electrons. So how many unpaired electrons are there? I see 3. Another way of looking at it is 8 minus 5 is 3, because the second shell can hold up to 8 electrons, and it needs 3 more to make 8. So now that we know the electrons that are traveling around the nucleus, that gives us a clue to how actually bonds are formed. Bonds are formed because of the number of electrons that are outside of the shell, and this tells us how many potential bonds can be formed. So to start this so that I can illustrate it for you, we're going to talk about covalent bonds. When I think of covalent bonds, I actually think of a Hercules handshake. Yeah, you're right, a Hercules handshake. Hercules, when he went walking around and meeting people, he gave a strong, firm handshake. And that's what a covalent bond is. It's the sharing of electrons. And the sharing of electrons makes for a very strong bond. So, why do atoms share electrons? Well, they want to have a stable shell. The valence shell needs to be stable, so it needs to be filled with either 2 electrons in the first shell or up to 8 electrons in the second and third shell. So they're going to start sharing electrons. So covalent bonds form when unpaired valence electrons are shared by 2 atoms. And this effectively gives each atom a full outer shell. It makes them stable. One example is hydrogen gas. So what is hydrogen gas? Hydrogen gas is formed by 2 hydrogen atoms. Well, each hydrogen atom has 1 electron, but the first shell holds up to 2 electrons. So each of the atom needs 1 more electron. But if they share their electrons, then now they have 2 electrons, and they both satisfy the 2 electrons that are needed to make each atom stable. So by definition, what is a molecule and what is a compound? A molecule is a substance held together by covalent bonds, and a compound is a molecule also, but the big difference is that different elements are held together by covalent bonds. So let's go back to hydrogen gas. Hydrogen gas is made up of 2 hydrogen atoms, so it definitely is a molecule, but it's not a compound because it doesn't have different elements. It only has hydrogen. Now, there's 2 types of covalent bonds. There's nonpolar and polar covalent bonds. So what's the difference between the 2? That means that either electrons are shared evenly between atoms or they're not shared evenly. If they're not shared evenly between 2 atoms, it's because one atom is electronegative. So what does electronegative mean? It means that it's a very strong atom and the nucleus pulls electrons towards them. So if we look at CHON, C-H-O-N, the 4 elements that make 96% of all organisms, of those 4, oxygen and nitrogen are electronegative. So every time you see oxygen and nitrogen in a compound, you know that they're not going to share their electrons equally. And when they don't share their electrons equally, they form polar covalent bonds. And polar covalent bonds means that there's going to be a charge. Like when I think of polar, I think of a magnet, and a magnet has a positive and a negative side. So they're going to form polar covalent bonds. So let's go over this again. There's two types of covalent bonds: non-polar covalent bonds and polar covalent bonds. If you have a non-polar covalent bond, there's not going to be an electrical charge because electrons are being shared equally between two atoms. In other words, the bond is symmetrical. A classic example are two electrons being shared by carbon and hydrogen. They're going to share the electrons equally, and therefore it's neutral. There is no charge. It's non-polar. Then the other type of covalent bond is a polar covalent bond. Electrons are shared unevenly. And remember, oxygen and nitrogen are electronegative. They pull electrons towards them. Therefore, electrons are shared unevenly. And because of that, there's a negative and a positive charge. So, a classic example would be electrons shared between oxygen and hydrogen. They're not shared evenly, therefore there's a charge, and they're called polar covalent bonds. I love figure 2.5 because it shows exactly the difference between nonpolar and polar covalent bonds. So we've seen hydrogen gas. So the two hydrogen atoms are sharing the electrons equally. They're in the middle, it's symmetrical. They're neutral and there's no charge. This is an example of a nonpolar covalent bond. So what's a polar covalent bond? A classic example is water, H2O. Well, oxygen is electronegative. Oxygen is strong, and notice that it's pulled the electrons towards oxygen. So electrons have a negative charge. So you're going to see a squiggly line with a negative. That's delta negative. That means the side that has oxygen has a negative charge, and the side of water that has hydrogen will have a positive partial charge. So all that's left for hydrogen is a positive proton, giving it a positive charge. So notice electrons are shared unevenly, there's a charge, and therefore it is a polar covalent bond. You know what, guys? Which one is the stronger of the two? Nonpolar or polar? The answer is definitely nonpolar. A nonpolar is a much stronger bond than a polar covalent bond. Okay, so it says here an atom in a molecule with high electronegativity is going to attract electrons, and it's going to hold them more tightly, and it's going to hold them closer to the atom. So this is called a partial negative charge, like we saw with oxygen and water. The other atom will have a positive charge because the electrons are not there. The next kind of bond that I'd like to talk about is ionic bonds or ionic bonds. So what is an ionic bond? I think the operative word here is a transfer of electrons. So instead of sharing electrons like we see in covalent bonds, in ionic bonds, actually electrons are transferred. So notice now atoms may lose or gain electrons. So when an atom loses or gains an electron, it's called an ion. And there's two types of ions. It can either be a cation or an anion. An cation has a positive charge and an anion has a negative charge. Okay, my little mnemonic device is the word cation has a T in it, and that T reminds me of a positive charge. So that's how I know that a cation has a positive charge, whereas an anion must have a negative charge. Ionic bonds are the attraction between oppositely charged ions. The classic example is sodium chloride. Well, what is sodium chloride? Sodium chloride is table salt, you know, the white stuff that you put on the table to actually make your food more tasty. And if you guys use fish sauce, like I've bought fish sauce, like the Asian fish sauce, and you'll see like beautiful little crystals inside. And those crystals are actually sodium chloride crystals. Well, how does it form? Well, if you look at the diagram in figure 2.6, you'll notice that sodium has 3 shells, and sodium is found on the 3rd row of the periodic table. And notice there's a lone electron in that 3rd shell. Well, it means that it needs to find 7 more electrons to form covalent bonds. That's going to be sort of difficult. Wouldn't it be much easier if that lone electron was transferred? And in this case, it's transferred to chloride. So if you look at chlorine in the second part here, chlorine only has 7 electrons. It needs 1 more. So that transfer of an electron from sodium over to chlorine means that sodium has 1 more proton than it does an electron after the transfer. So it is definitely a cation. It has a positive charge. Chlorine is gain an electron, and an electron has negative charges, so it has 1 more electron than it does protons, so it becomes an anion. And keep in mind, now we have positive and negative charges, so these positive and negative charges are attracting each other and forming an ionic bond. So it says here there's a continuum between ionic bonds, ions, and electron sharing continuum. So it's talking about the strength, and there is a continuum. So it says there's from equal sharing in nonpolar covalent bonds, then we go to unequal sharing in polar covalent bonds, and then we go to the complete transfer of electrons in ionic bonds. So here are some examples. I love this. Hydrogen gas and methane, which is CH4, these are nonpolar covalent bonds. In other words, the electrons are shared evenly and they're symmetrical and there's no charge. And then we have ammonia and water. Well, you guys already know that nitrogen and oxygen are electronegative, and therefore they pull electrons toward them, and electrons are shared unevenly. And you can see now there's a charge to actually these molecules. There's positive and negative charges. And then lastly, we have the transfer of electrons, like in sodium chloride. So now we have both positive and negative charges, in other words, cations and anions, and these opposite charges attract each other. Okay, so simple molecules can be formed from carbon, hydrogen, oxygen, nitrogen, and oxygen. In other words, from CHON. So it says here, how do we know how many bonds can be formed? Well, it's going back to the valence, the outermost shell, the valence shell, and we look at the number of valence electrons in valence. Because remember, atoms want to be stable. So they either need to share electrons or transfer electrons to become stable. So it says here atoms with more than 1 unpaired electron can form multiple single bonds, they can form double bonds, or triple bonds. So keep in mind, for every bond that's formed, you need 2 electrons. I promise you this will be a test question. So how many electrons are involved in a double bond? Okay, well, a double bond is 2 bonds, and if each bond holds 2 electrons, then 2 plus 2 is 4. In a triple bond, 6 electrons are being shared. Okay, so here are some examples in figure 2.8. In figure 2.8, we see that water and ammonia have single bonds. So does methane. When we look at double bonds, CO2 has double bonds. And you can see that there's a total of 4 electrons being shared between oxygen and carbon. And then our atmosphere is made mostly of nitrogen gas. And you see here that nitrogen gas is made of a triple bond. In other words, 6 electrons are shared so that the outer shell has a total of 8 electrons. Now, it is true that the molecule shape often dictates its behavior, and you already saw that water that has a positive and a negative side has partial negative and partial positive portions. Looks sort of like Mickey Mouse ears. And that Mickey Mouse shape is really important in the way that it reacts. But you know what, guys? Let's save the geometry of molecules for your chemistry class. So I won't be testing you or assessing you over the geometry of simple molecules. So let's skip this. Okay, we'll skip this also, and let's go over to representing molecules. So we can represent molecules in 3 different ways. We can represent it as a molecular formula, and here we see H2O, which is water, and CH4, which is methane. You know, like swamp gas, or the gas that comes out from your own basement, you know, the basement in your body. Then we have structural formulas, and this shows the number of bonds that are in between the atoms. And so we can have ball and stick models or space filling models also. I love figure 2.10 because in 2.10 it gives you examples of molecular, structural, and ball and stick models and space filling models. And these are several different ways of explaining what actually a molecule looks like. And notice that we use all different forms all the time. So here they give examples of methane, ammonia, water, and carbon dioxide. Okay, so now let's start talking about the properties of water. And remember when I introduced this chapter, I said that water was really important? Well, most chemical reactions occur in water, but isn't it true, guys? Isn't it true that most life is made mostly of water? You know, the one thing that happened to me, it's been a long time, but my mother passed away over 20 years ago. And I remember when she died, we decided to cremate her. And at her funeral, I noticed that people were picking up her ashes and they were sort of bouncing the ashes in their hands. And I quickly realized that they were trying to guess how much her ashes weighed as to opposed to what was her weight when she was alive. In other words, they were trying to figure out her water content. So water is very critically important to life itself, and it's the place where most chemical reactions occur. So some terms that you need to know are solvent, solute, and solution. So what is a solvent? Well, solvent is the liquid portion. So water is a solvent. Well, what's a solute? Solute is the chemical that is dissolved in the solvent. So let's say you're having coffee in the morning that has sugar and milk. All those chemicals in the water, that's the solute, and the solvent is the water, and together they make a solution. Or what about when you're making spaghetti? Isn't it true that you boil water and you put salt in it? The water is the solvent. The salt that you put in the spaghetti water is the solute. And the two of them together is a solution. Okay, we've already realized that water is a polar molecule. Why is it polar? Because it forms polar covalent bonds. That means that the electrons are not shared evenly. And when they're not shared evenly, there's a charge. There's a partial negative charge and there's a partial positive charge. So that means that water is like a magnet, you know, like the magnets that you put on your refrigerator. And I think you intuitively know this. Why do you know this? How did the Grand Canyon form? Because water is a magnet and it took out all of the minerals from the rock. Just everything started sticking to it because it has partial positive and negative charges. And for that reason, it started pulling out the minerals from the rocks, and voila, you have the Grand Canyon. Water molecules also interact with each other, and now we're going to talk about the third type of bond. So far we've talked about covalent bonds, we've talked about ionic bonds, and now we're going to talk about hydrogen bonds. So what are hydrogen bonds? These are weak electrical attractions between hydrogen bonds. So they're called a hydrogen bond, and you see that they happen in between water molecules. So if you look at figure 2.11, you see that there's this dotted line that's covered by yellow. That interaction, that's a hydrogen bond. So they're weak electrical charges. So let's take a closer look. The hydrogen side of a water molecule has a positive charge. The oxygen side that has all the electrons has a negative charge. So opposite charges attract each other. So notice in diagram B, you see that hydrogen is attracted to oxygen. So therefore you see that dotted line covered in yellow, that's the hydrogen bond between two water molecules. By the way, this is going to be your extra credit question for your first exam. If you can draw several molecules, water molecules, and show the hydrogen bonds, you'll get 5 extra credit points on your first exam. Okay, so now that we know that water molecules interact with each other, we need some new vocabulary words. And the first word is hydrophilic. So what does hydrophilic mean? Well, hydro means water, and philic means loving. You know, like this Philadelphia. Philadelphia means the city of brotherly love. So hydrophilic means water loving. So that means that atoms that interact with water are called hydrophilic. Well, water has a charge to it, so it makes sense that water interacts with other molecules that also have a charge, or it interacts with ions. So this is how I remember it. Birds of a feather flock together. Water has a charge, and it likes to interact with other molecules that also have a charge. So water likes to interact with ions or molecules that have polar covalent bonds. So here's an example of water interacting with sodium chloride. So now you understand why once you put salt into water, it dissolves, and you never see it dissolves, and salt crystals never form until all of the water evaporates. So why is that? Because the minute the sodium and chlorine molecules disassociate, sodium has a positive charge and it's attracting water. The chlorine molecule has a negative charge, and notice it too is attracting water. So water is surrounding each of these, and that's why it stays dissolved in water. Another word that you need to know is hydrophobic, like a phobia. If you have a phobia, it means that you hate something. So hydrophobic means water hating or water fearing. So if you have a non-polar covalent bond, that means it's symmetrical and there is no charge. So then it's not going to interact with water that has a charge. So hydrophobic molecules are usually non-polar molecules that have non-polar covalent bonds. I love this example in figure 2.13. You know what this reminds me of? It reminds me of two things. I'm thinking about the Gulf of Mexico and an oil spill. Well, what is oil? Oil is a hydrocarbon. That means carbon and hydrogen bonds, and they're sharing their electrons equally, so they're symmetrical, and because of that, there's no charge. Well, if there's no charge, then they're not going to interact with water because water has charges. This picture could also remind me of like a salad dressing. You know, like an oil and vinegar, an oil, water, and vinaigrette. So when you put oil in a vinaigrette, you see like the little globules of oil. How come they're not interacting with the vinegar and the water? Because they're sharing their electrons equally. And because of that, they have no charge. So it's a hydrophobic interaction. Okay, so water is a small molecule, but it's a mighty molecule. So what makes it so unique? This almost looks like a test question. It's small in size, it's bent, it has a high polar covalent bonds or highly polar covalent bonds, and it has overall polarity. When we say that it has overall polarity, we mean that water is like a magnet. Again, it has positive and negative charges, and it's pulling everything in sight that also has a charge. So when we say that it's pulling everything in sight that has a charge, what do we call that? So next I'd like to talk about cohesion, adhesion, and surface tension. Okay, so the one thing that you need to know is water's sort of unique. I can't think of any other compound. It is denser as a liquid than it is as a solid. And so there's a mistake here in the PowerPoint, because you know that ice floats. So ice is a solid form of water, and notice that it's less dense than as a liquid. And the other thing about water is that it absorbs large amounts of energy, and I'll talk about that in a little bit. So what is cohesion? Cohesion is the binding between like molecules. So water binds to itself. Okay, so we saw the hydrogen bonds in the previous figure. So this results in surface tension. But you know, the other thing that I think about is like when you're pouring water into a graduated cylinder and you have the meniscus, where you see that water goes up on the sides and then down in the middle. Well, why is water being pulled down in the middle of the graduated cylinder? When we're measuring something, we're measuring volumes in lab, and that's because the water molecules are actually connecting to each other with hydrogen bonds, and they're pulling the water level down. What is adhesion? Adhesion means that water's sticking to the sides of the graduated cylinder, and that's why you see sort of that curve at the surface. So water likes to also bind to different kinds of surfaces. It binds to plastic, glass, it binds to your skin. I love this example. See, here you can see the meniscus that I was trying to talk about. So notice that curvature at the very top. So why is that? Because of adhesion and cohesion. Adhesion means that water's sticking to the walls of the test tube, and cohesion means it's being pulled down in the center because of the hydrogen bonds. And in figure B here, you see that water has a high surface tension. That means it's sticking to each other. And this wolf spider is sort of religious because it can walk on water. But why can it walk on water? Because water is connected by hydrogen bonds. So therefore it has high surface tension. See, water is denser as a liquid than as a solid, and this slide is correct. So keep in mind that when water freezes as a solid, it is actually floating on water. Like I think of icebergs, right? Or what about ice cubes? So keep in mind oceans. When oceans freeze, don't they freeze up at the top? And underneath you have water. And that's why at the Arctic you have all kinds of life form, even though the top of the surface is frozen. So really, why is it that water's more dense as a liquid than as a solid? Because if you look at figure A here, it says water molecules form a crystal lattice. Guys, when you look at that crystal lattice, can't you see that the hydrogen bonding in between the water molecules has really sort of like extended? So now the water molecules are further away from each other, and because of that, water is less dense as a solid. If you look at frame B, you see that as a liquid, the hydrogen bonds are different lengths, and they've not extended themselves in a crystalline pattern. And so therefore they're much denser, they're closer together, and therefore in a liquid, water is more dense. So in the last frame you see that that's the reason why ice floats, and it all goes back to hydrogen bonding. Okay, water has a high capacity for absorbing energy. For the life of me, I had such a hard time understanding this, but I'm going to give you some examples. So water has high specific heat. So it says, what is specific heat? It's the amount of energy needed to raise temperature of 1 gram of a substance by 1 degree Celsius. Well, it takes a lot of energy to raise 1 gram of water by 1 degree Celsius. Well, why is it? Again, it goes back to the hydrogen bond. It takes a lot of energy to break the hydrogen bond. But you know what I think about? I think of all those beautiful people that live like in California. They live right there by the ocean. And I'm always really jealous. Like, how can they wear designer sportswear and go out jogging and they don't sweat or anything? And I just want to hit them and slap them because their hair is nice and dry and their makeup is in place. Well, why is that? It's because the ocean is moderating temperature. Remember, water stores a lot of energy, so we don't see the great fluctuations in temperature like we see in the desert. And this has to do to the specific heat of water. So the oceans are holding a lot of energy because there's a lot of hydrogen bonds. Okay, now what is heat evaporization? This reminds me of the desert. Heat evaporization is the energy required to change 1 gram of a substance from a liquid to a gas. So isn't it strange that here in the desert it can be 110 degrees outside, but the minute you get out of the shower or a swimming pool, you're freezing to death? That's because of heat evaporization. All of the energy from your skin is being absorbed by the hydrogen bonds and broken for the water to evaporate from your skin. You know how in Mexico they have the clay jugs and the water inside the clay jug is nice and cold even though it hasn't been in the fridge? This is due to heat evaporization. In other words, here it's so hot, but to break the hydrogen bonds for water to go from a liquid to a gas state, it's stealing that energy, and when it does, it's cooling off. So we use that for our evaporative coolers in our houses. Okay, next I'd like to talk about chemical reactions. So what is my definition of a chemical reaction? It's really quite a simple one. It's the breaking of bonds and the forming of new bonds. That's a chemical reaction. Breaking bonds and forming new ones. So if you look at a chemical reaction and you look at an equation, on one side you have reactants and on the other side you have products. I promise you this will be a test question. So it gives an example here of water. So if you take a look at the first equation, it says H2O in a chemical reaction can be broken down to 2 ions. The hydrogen ion, which is H plus, and the hydroxyl ion, which is OH minus. Well, this is going to lead us to acid-base chemistry. When I think about it, water is the only compound that I know that has both an acid and a base part to it. So this sort of explains the beginning of acid-base chemistry. So what is an acid? An acid is any substance that gives up protons. Protons, okay, so I'm going to tell you something. In your book, they use the word protons, but oftentimes they're looking at the hydrogen ion. So why is the hydrogen ion called a proton? Because H plus means that atom has given up its only electron. And when it's given up its only electron, well, what's left in the nucleus? Just a proton. So an acid is a substance that gives up protons, or you can say it gives up hydrogen ions. What's a base? A base is a substance that acquires protons or that acquires hydrogen ions. The next thing that your chapter talks about is molecular weight, moles, and molarity. Now, why are there different ways of expressing concentrations of protons? Well, it's because you already realized from the periodic table that there are atoms, but aren't they different in size? Hydrogen is the smallest, and as you zigzag through the periodic table, each of the atoms gets larger and larger and larger, and you know this because the mass number increases. Also, the number of protons and the number of neutrons increase. So, how do we calculate reactions, or how do we calculate the weight? So it says here the molecular weight of a molecule is the sum of atomic weights of all of the atoms. So if you were to look at H2O, the atomic weight of hydrogen is 1, and the atomic weight of oxygen is, take a look. Look up in the periodic table. And if you add them all up together, you're going to find the molecular weight. Now, another way of expressing a concentration is through a mole. Regardless of size, 1 mole always contains 6.022 times 10 to the 23rd molecules. It doesn't matter whether it's hydrogen, oxygen, carbon, or nitrogen. One way of describing a concentration is by mole, so that you don't have to worry about the size of the atom. And the last way of expressing a concentration is through molarity. Most of the time, substances are actually dissolved in water. So, what is molarity? It's the concentration of a substance in a solution. And that solution is, so molarity is a number of moles per liter. For this class, I'm going to be honest with you guys. I want you to be aware of it, but we'll save all of this for chemistry, and you really won't have any questions on the exams on moles, molarity, or any other type of concentration. But you will have questions on pH or acid and basic solution. So when I think of pH, my definition of pH is the power of hydrogen. What do I mean by that power of hydrogen? Well, pH is the negative log of the molar concentration of hydrogen. So it is a logarithmic scale, and it's sort of counterintuitive. Isn't it true that the pH scale goes from 0 to 14? 7 is neutral, and if the pH is below 7, then it's acid, but if the pH is above 7, it's a base. But why do I say that it's counterintuitive? Because remember, acids have more protons to release. But according to this, a proton or a hydrogen ion, it's an increase, but keep in mind this is a negative scale, so that's why it's counterintuitive. So this slide reiterates that acids have a pH of less than 7 and bases have a pH of greater than 7. A new word here is buffer. So a buffer says it protects against changes in pH. So I'm going to give you 2 examples. Our blood is basically at close to a pH of 7. So it doesn't matter if I eat a lot of acidy food or if I eat a lot of food that is basic. What's going to happen is my blood it won't change. It won't change the pH. So we can say my blood is buffered at 7. You guys know that I'm an Aggie by training, so our desert soils have a pH of 8. I could buy a bottle of vinegar and pour it on the soil. We know that vinegar is an acid, and when I pour it onto the soil, you can see it frothing. But if I take a pH meter after about an hour, I still see that the pH stays at 8, no matter how much acid I pour on it. That means the soil is buffered at a pH of 8. It won't change. It's resisting a change in pH. So it says here buffers are important because it helps maintain homeostasis. In other words, it helps maintain constant conditions. I love this drawing here because it explains some of the basic pHs and things that you see every day in your life. Notice that human blood is in fact close to a pH of 7. So is milk. Urine is a little bit acidic. So is coffee, tomatoes, and lemon juice. So people that have stomach problems like myself, that's why we can't drink black coffee or I don't get too excited about wine because it hurts my stomach. But notice up at the top, there's milk of magnesia, and that it has a pH between 10 and 11, baking soda, and that's often used by people like me to neutralize stomach acid. This next section in chapter 2 is about getting back to the beginning of this chapter. What is chemical evolution and how might it have begun? So there's two basic models. There's the atmospheric model and then there's the deep sea hydrothermal vent. So what does the atmosphere model say? It says that there were simple molecules in the atmosphere, and with energy they started colliding, and with energy they formed larger molecules. So these simple molecules were H2O, CO2, and nitrogen gas. In the second model, in the deep sea thermal vents, it says that there were a lot of these gases, but deep down in the ocean where there's a lot of thermal activity. And this thermal activity provided the energy for these small molecules to collide and form larger molecules. So how is it that chemical reactions occur? So remember, what is a chemical reaction? Chemical reaction is the breaking of bonds and the formation of new ones. So in this chemical reaction here, we see that CO2, which is carbon dioxide, plus water forms carbonic acid. What is carbonic acid? CH2O3. This is such a very famous formula. This is the formula that shows why there's acid rain. So when we have a lot of CO2 in the atmosphere and it rains, we can form carbonic acid and form acid rain. So it says here there are the same number of atoms on each side, but notice bonds have been broken and reformed to form carbonic acid. So this is a chemical reaction. So it says here, how do chemical reactions happen? And so here we see water as a liquid changing to water as a gas. And you know, for it to change from one state to another requires a lot of energy. And in this case, it absorbs a lot of thermal energy. That's why when we get out of a shower, even on an extremely hot day, it steals all the energy from our skin, because to go from a liquid to a gas, you have to break a lot of hydrogen bonds. So it needs a lot of energy. So that brings us to two more terms, and you'll need to know this for the exam: endothermic and exothermic reactions. So endothermic, if you look at endo, it means going in. Thermic is temperature, or another way of expressing energy. So energy coming in. So energy needs to come in for the reaction to occur. What does exothermic mean? Exo means to exit. In other words, energy is released from the reaction. So exothermic reaction. So now the question is when we talk about energy, what are we really talking about? So it says energy is the capacity to do work or to supply heat. And that's why we look at thermal energy. That's one way of measuring it. So there's two ways of looking at energy: potential energy or kinetic energy. Well, what is potential energy? It's stored energy. It has to do with the position. P is for potential. P is for position. So where do you find energy in a molecule? Well, energy in a molecule is potential energy, and that energy is stored in the bonds. It is stored potential energy in the chemical bonds. So when the bonds are broken, what happens? It's going to release energy. Then the second type of energy is kinetic energy, and I always think of kinesiology, physical movement. So energy, the movement the energy of movement. You'll have to know potential and kinetic energy for the exam. So it says in molecules, potential energy is related to the position of shared electrons in covalent bonds. So when we were talking about bonds and where the electrons were, we were also talking about what? Potential energy. If the bonds and the electrons are shared equally or symmetrically, they share a lot of energy. If they're not shared equally, then they have a weaker bond, and that would be in a polar covalent bond. So now we can look at the way that electrons are shared, and we can actually see whether the bonds are strong or weak with regard to chemical energy. So let's take a look at this. This is looking at the length of the bond, and it's also looking at the position of the electrons. So notice in OH, where oxygen is very electronegative and actually pulling the electrons towards it, that's a polar covalent bond. So notice here it's unequal sharing. Nitrogen in an NH bond also is pulling the electrons to one side. And then we have a carbon-hydrogen bond. So notice at the very bottom you see an increase in potential energy. So the more symmetrical the electrons are, the more that they're shared equally, the greater increase in potential energy. So in other words, non-polar covalent bonds where there's equal sharing of electrons has greater potential energy than those bonds that have unequal sharing or polar covalent bonds. So kinetic energy is the energy of motion. And so we can also think of this as thermal energy. And so temperature is a measure of this thermal energy. To be honest, guys, I always think about sumo wrestlers or like sweaty sumo wrestlers. They're moving around in that little circle and they're really nice and sweaty. So that is an example of kinetic energy. And so heat is a measure of thermal energy being transferred between two objects. And in my mind, I guess I'm thinking about sumo wrestlers. So it says here, if an object has low temperatures, its molecules are moving slowly, and that's why we perceive it as cold. If an object has a high temperature, it is moving rapidly, and that's why we perceive it as hot, because it has high kinetic energy. When we talk about energy, we also have to talk about the first and second laws of thermodynamics, and you'll have to know this for the exam. It says here that energy is conserved. Energy cannot be created nor destroyed. It can only be transferred or transformed. So energy transformation is the heart of chemical evolutions. So molecules of the early Earth were exposed to massive energy inputs. So I'm going to be honest with you. If chemical evolution is going from small molecules to larger molecules, then those are going to be endothermic reactions. In other words, massive amounts of energy were needed to build large molecules. And that sort of makes sense because energy is stored in the bonds. So you need to get the energy from somewhere. Those were endothermic reactions. In this one, it says here, chemical reactions are spontaneous if they proceed without any continuous external influence. In other words, no energy is needed. In other words, they're not endothermic reaction. The spontaneity of a reaction is determined by two factors. Products are less ordered than the reactions, that's entropy, or products have lower potential energy than the reactants. So let's look at a spontaneous reaction. What does that mean? Products are less ordered than a reaction, than the reactants. So keep in mind, small molecules have less potential energy. Large molecules with more chemical bonds have greater potential energy. So if large molecules are broken down into smaller ones, then they will have entropy. It increases disorder. So to go from large to small molecules is disorder, and another name for that is entropy. Keep in mind that small molecules have less potential energy because they have fewer bonds. So when you're breaking something down from a big molecule to a large molecule, there's a release of potential energy. So this is what we mean by products having lower potential energy than the reactants. I love this example here. This is one of those like a Led Zeppelin, and notice here it's filled with hydrogen gas, but notice it becomes very explosive. So notice that hydrogen and oxygen both share their electrons equally, but when actually there's a reaction and there's an explosion, it's going to form water and a release of energy. And notice that the electrons now, instead of being shared equally, are now polar covalent bonds. So this is that release of energy. So now this is actually an exothermic reaction, and you can see the release of energy as heat and light in the picture. And that's why we don't have these balloons anymore as a mode for travel. The second law of thermodynamics says that entropy always increases. You know from the previous slides that entropy actually refers to disorder. In other words, disorder is always increasing. I'll give you an example. When my children got older, I would say, it's time to clean your room on the weekends, and they would tell me, no, Mom, I don't have to clean my room because actually of the second law of thermodynamics. Entropy or disorder is always increasing. So it says here, physical and chemical processes proceed in the direction that results in lower potential energy and increased disorder. In other words, large molecules are being broken down to smaller molecules with fewer bonds and less potential energy. I love this reaction here. Here's one of my favorite molecules of all time. It's glucose. It even makes my mouth like get all excited just to think about sugar. So glucose and oxygen is broken down into CO2 and water. So notice we're going from a highly ordered molecule, glucose, which has a lot of covalent bonds, to very small molecules, CO2 and water. So we're going from high potential energy to low potential energy, and I'm looking at the size of the molecules and the number of bonds in between the atoms. So model systems for investigating chemical evolution. So remember we talked about the atmosphere and deep sea thermal vents. So this is sort of a continuation of this idea. So there's this prebiotic soup model and the surface metabolism model. So what is this prebiotic soup model? Well, and it has a lot to do with the atmosphere, that the oceans, that there was this rain and energy in the atmosphere, and this is where molecules went from small molecules to large molecules. Now notice here there always has to be a source of energy for endothermic reactions. In the surface metabolism model, it says dissolved gases came into contact with minerals lining the walls of deep sea vents, and this energy was used to form larger molecules from small ones. Again, a lot of energy needed for endothermic reactions to go from small to large chemical molecules. Okay, now one of the classic experiments is done by Stanley Miller. The other reason why I like it, because it was done by his chemistry students. So this was trying to prove that simple molecules can in fact form larger, more complex molecules if there's an energy source. So in this Stanley Miller experiment, you see that there's a contraption here, and it looks like in the old Frankenstein movies. So the lower bulb represents the ocean, and the upper bulb up above represents the atmosphere. The first time they did this experiment, water circulated through the system, like it evaporated and the water vapor went up into the atmosphere in the bulb, then it condensed and went back into the ocean. And you see that there's some stopcock so that they could take some samples, and they found that nothing was happening. So then they redid the experiment and they added electrodes that you see in the atmosphere. In other words, the source of energy for endothermic reactions. And once they added the electrodes, they noticed that the fluid even changed color, and this indicated that actually more complex molecules were being formed. So this, in a sense, proved that there was chemical evolution and that more complex molecules can be formed from small, simple molecules. So again, the origin of life experiment shows that if you have a source of energy, like electrical charges to represent like lightning in the sky and heated water, that if you have energy sources, then you can form large molecules from simple ones. So it says here we also need energy. So we also get energy from light, and this energy is called photons. And these photons can actually break molecules down, and then new ones can be formed. Because remember, that's what a chemical reaction is. It's the breaking of old bonds and making new ones. So here they show that photons can actually break bonds, create radicals, that is, free atoms, and then these atoms can form new bonds. And here, this gives you an example of the prebiotic soup model or the atmospheric model. So notice it's in the first frame, you see that there's very simple molecules, but when light, energy, and heat are added, that you see that simple molecules go to intermediate sized molecules, and these intermediate sized molecules actually form large complex molecules like amino acids and sugars. It says here, in addition to having light energy in the form of photons, you can also have a catalyst. And this would be in the second model, the deep thermal vent model, where minerals act as a catalyst. So the presence of minerals actually could speed up reactions. So in this model here, you sort of see the same thing, except that you see that a lot of these simple molecules are actually attached to minerals on the ocean floor. And they're actually condensed and closer together and reacting, so they go from simple to intermediate to more complex models, with the help of minerals acting as a catalyst. In other words, speeding up the reaction. The last part of this chapter talks about organic molecules. Why is that so important? Because all life is made of carbon here on Earth. So carbon is the backbone to all organic molecules. So when we talk about organic compounds or organic chemistry, we're talking about the study of those compounds that have carbon, and carbon is the backbone. So why is carbon so important? Well, it's abundant, and do you remember that in its outermost shell, its valence shell, that there's 4 electrons, and it needs 4 more? So like it's a great connector because it can form 4 more bonds. So it makes sense that we are made mainly of carbon. So in this first one, we see a hydrocarbon. This is octane, and this is what we put in our gas tanks. And in B, we see that there's sugar, glucose, and glucose is a ring, C6H12O6. And you know I love glucose. Okay, the last thing that you need to look at is you need to look at functional groups, because in the upcoming chapters, you're going to see that we're going to talk about very, very large molecules. So how do we know about the characters of these molecules? Well, the only way that we can know about the character of these molecules and the potential for forming new bonds is by looking at their functional groups. So some important functional groups are amino groups, carboxyl groups, carbonyl groups, hydroxyl groups, phosphate groups, and sulfhydryl groups. I love this diagram, and the picture is much better in your books, but it shows you each of these groups. And actually, we'll be looking at these as we look at macromolecules.